Okay, thank you. This is Bob Crivello with NVIDIA Corporation. I'm on the Solution Architecture team, and this is part of a continuing series of CUDA training topics. On behalf of NVIDIA, I'd like to thank the organizations at Oak Ridge and other organizations like NERSC who have made this possible and provided all the logistics for us to do this. We're very appreciative of that. I hope you will find this session useful. You're welcome to ask questions on chat, and I will also pause probably at 2 or 3 points during the presentation to see if there are questions that people have if they wish to come off mute, and I'll probably take a quick look at chat at that point. This presentation today is probably going to be a little bit longer, perhaps, than some of the ones that we have done in the past. So I'm anticipating we will definitely take more than an hour and probably could very well be 90 minutes. One of the things that is going to make this a bit of a longer presentation today is that we're going to cover 3 topics: CUDA error management, Compute Sanitizer, which is a tool, and then CUDA GDB, which is another tool. During the CUDA GDB session, I'm going to do an extended demonstration or walkthrough of how to debug applications using CUDA GDB. So there will be a live demonstration, and that takes a fair amount of time to cover all of the topics that are really needed so that you are enabled or able to use CUDA GDB with enough capability to be able to debug applications. So that's going to make this session a little bit longer. As a result of that, we do have homework prepared for you. It's available now on the GitHub site. However, I don't think we're going to have time to walk through the homework. We've done that a couple times in the past for certain sessions, but I don't think we're going to have time to do that today. I'd also like to introduce some of my colleagues. They may or may not have joined yet. One of them is Max Katz. Another is Robbie Searles, and the third one is Matt Stack. They are all on the Solution Architecture team as well, and they have all contributed to this training series as well. So I appreciate their participation. So we're going to start out with error management. And the overall idea of this presentation today is to make you a better CUDA programmer in the sense of being able to sort out problems that exist after your application is already written. So it's not really teaching you how to program today. What we're teaching you how to do is once you've got your program written and you're running it, and perhaps, let's say you're not getting the right results or you're witnessing strange behavior, we want to give you the tools and knowledge necessary to be able to sort that out and understand what's going on. So in that vein, I believe the right place to start is actually a fairly mundane topic, which is, I would refer to this as proper CUDA error checking. We'll call it error management. And the basic idea here is that all CUDA runtime API calls return an error code. So what is a CUDA runtime API call? It's an example of one is what you see here, CUDA set device. In other words, any library call that begins with the letters CUDA that you're using without providing a prototype for. In other words, this is not a function that you wrote. Almost certainly that's part of the CUDA runtime API, and there's plenty of these that you've run into already if you are a CUDA programmer or if you've been following along in this series. CUDA set device is just one of them, but there's plenty others. CUDA stream create, for example, is another one that has to do with stream creation. And there's plenty of these. Every single one of these API calls returns an error code that is of a particular enum type, an enumerated type called CUDA error _T. And unfortunately, what we witness in this development arena is that many times people simply ignore that. In other words, they say CUDA set device, just as you see written here, without capturing the error code in a return variable. And that is, we could say it's kind of a lazy practice or a sloppy practice. I'm not going to try and get into really any judgment of it. However, I will say that if you are having trouble with a CUDA code, this is the place to start. If you have not done rigorous, proper error checking, rigorous means that you're capturing every single one of these on every CUDA runtime API call and handling it appropriately, printing it out if it's not a no error indication or whatever the case may be, however you'd like to handle it. If you're not doing something explicit when this return error code is not of the enum type or the enum token CUDA success, then you're really not doing rigorous proper CUDA error checking. And the first suggestion that I'm going to have for every CUDA programmer who is having trouble with the CUDA code of any sort is to make sure that you are doing rigorous, means every single opportunity, proper, capturing the error code and doing something appropriate with it, CUDA error checking. There's obviously other types of enum return types. There's literally hundreds of them. We're not going to cover them all by any means. For example, another enum token is CUDA error memory allocation. And so if this was, for example, a call to CUDA malloc, and the CUDA malloc call was successful, you'd expect to see the CUDA success token returned in the error return variable. But if it was unsuccessful, let's say you were out of memory and you didn't have enough space to allocate what you're requesting, then you'd expect a return token like CUDA error memory allocation. Of course, the token is really something like just a number underneath the hood. A enum type is basically just a list of numbers ultimately underneath the hood, at least in C and C++. And so we don't want to just print out a numerical error code. And even something like CUDA error memory allocation might not be that as useful as we'd like it to be. And so we have a built-in CUDA runtime API function called CUDA get error string, which takes a CUDA error t enum type value and converts it into text, English text, human readable string. And so this is strongly encouraged as well. At a minimum, if you get something other than CUDA success, make some notification of that, right? That's a minimum, that's the minimum necessary behavior that we would expect for anyone who's having trouble with a CUDA code. But beyond that, just to help yourself and help others, it's not a bad idea to wash that, so to speak, through CUDA get error string and print that out instead. And so I can't overemphasize this. The best practice is to always check these codes and handle appropriately. Just do it. We'll kick off our next section by noting that at least in the CUDA runtime API, when we do a kernel launch, and there's an example of the kernel launch syntax there at the bottom of the slide, that doesn't appear to be a CUDA runtime API call. It doesn't start with CUDA. In fact, I can name kernel name anything I want. And in fact, that by itself, as it stands, is not a CUDA runtime API call. Okay, so that doesn't return an error code. And we know that kernels, by definition, anything decorated with the global keyword returns a void type. So we're not going to get an error simply by trying to capture the return code of this. That's not the right way to do it. So we need to talk about kernel error checking and how that happens and how we should do it. So before we dive into kernel error checking, we should have to remind ourselves that CUDA kernel launches are asynchronous. This means that they're launched from the host thread, from the CPU code, and then they begin to execute essentially concurrently with whatever the CPU thread is doing at that point. We don't have any strong indication automatically in our CPU thread of when the kernel is complete. And furthermore, if the kernel were to hit an error that was the result of kernel code execution, that error would happen at some, let me just refer to as random point subsequent in our CPU code. And so what you could have happen is, as we see on the right-hand side, you could have host code that launches a kernel called dev. And on the right-hand side, we sort of pictorially indicated what that kernel might be looking like. And let's say that kernel hits an error, an execution error, okay? In other words, an error that occurred as a result of the device code in the kernel that's actually running at that time. Well, that error, even if we were to signal it back to the host code, that error would be signaled at some point in the host code, which is sort of non-deterministic or non-specific because of this asynchronous nature of CUDA kernel launches. And so what can happen, and what often does happen, is it will do some other innocuous CUDA runtime API call, like CUDA set device here, something that we would basically never expect to fail. Like if I have 4 devices, I might have a loop to set it amongst the 4 devices. And I expect that to be setting devices 0, 1, 2, or 3. There's really no reason. I can't think of a reason why that would fail. And yet, at some point during the runtime, I execute this CUDA set device and I check the return code because I was told to do that. And I get a strange error like error CUDA misaligned address or error illegal address, something like that. And so this is part and parcel of the fact that kernel launches are asynchronous, and even an execution error during a kernel launch is something that can be reported and will be reported by the CUDA runtime API, but it may be reported at some sort of, I'm just referring to it as a random point down the road as my CPU thread is continuing to do work beyond the kernel launch. And this can be confusing. It is confusing to get something like a misaligned address when you do CUDA set device. The two don't go together. They don't even make sense together. And yet this is the way the CUDA runtime API behaves. Once it has an error to report, it will report that error on the next CUDA call. So in order to handle these errors, we're going to have to think about this asynchronous nature carefully. And we're going to probably make some trade-offs in terms of the behavior that we would like to achieve with our code and the clarity of the error reporting that's going on. Okay, so let's talk about that trade-off. A typical kernel error checking example is given on the right-hand side. And the first thing that we want to point out is that a kernel launch can have two different types of errors associated with it. One called a synchronous error and one called an asynchronous error. The asynchronous error is exactly what we've been talking about for the last couple minutes. Okay, it's an error that occurs during CUDA device code execution. It occurs at some random point with respect to the behavior of the CPU host thread. And it's as a result of device code execution. A synchronous error, on the other hand, is an error that's detectable right at the launch. And I'm going to give you an example of that so we'll have an idea of what that means exactly. But it's something about the kernel launch itself that was detectable at the launch point, and therefore the kernel never launched. It was detectable right at the launch point. You asked for an invalid configuration, most likely, in your kernel launch parameters, those parameters that are in between the triple chevron syntax. You ask for something invalid at that point, and the runtime API says, no, you can't launch a kernel with 0 threads per block, for example. Okay, that would be an example of a synchronous error detectable right at launch. And so for these synchronous errors, again, remember the kernel launch is not by itself a CUDA runtime API call, and yet it can produce these synchronous errors. Therefore, in order to catch those, we're going to introduce an API function called CUDA getLastError, just as you see on the right-hand side. That is a CUDA runtime API call. It does, therefore, return the CUDA error T enum type. It will be captured in that variable. And when we organize our code this way, as you see on the right, the CUDA getLastError call would capture any synchronous errors as a result of the attempt to launch the dev kernel. But as we talked about previously, there are other types of errors that can be reported, those that occur during device code execution of the kernel. Those are asynchronous because the kernel execution is asynchronous to the CPU host thread. And therefore, we need another mechanism to capture those. Now, we've seen one already. If you continue to do runtime API calls in your application, sooner or later, if you continue to do that, and you have a kernel execution error as a result of the dev kernel launch, then sooner or later, the CUDA runtime API calls is going to report that. However, that doesn't necessarily give you the most clarity, because if your application is busy and doing lots of different things, it's not at all immediately obvious even which kernel launch caused that error. And so one of the things that you might want to do to help with error localization to improve the clarity of the error reporting is to make your kernel launches blocking. And there's a few different ways to do that, which we're going to discuss here on this slide. One of the ways is what you see on the right-hand side. We could simply issue a CUDA device synchronize call right after the kernel launch, and that will force the kernel execution to complete before the CUDA device synchronize call returns. And therefore, we can be certain that that CUDA device synchronize call would return any asynchronous errors associated with that kernel launch. However, this interrupts lots of things that we might want to do in our application, like have concurrency and asynchrony. Okay, so this isn't necessarily ideal, but you might want to define a debug macro that says, when I'm debugging my code, I'm going to put up with having each launch be blocking, and I'm going to get the error reported that way. Otherwise, when I think my application is working correctly, I don't define the debug macro, and this line essentially disappears. Another optional way to handle this is to set an environment variable that's listed at the bottom of the slide called CUDA launch blocking to 1. And when you do that, the CUDA runtime will obey that request, and it will make all of your launches behave as if they had an implicit CUDA device synchronize call after them. And what that means is that now our CUDA get last error call that we see on the right-hand side, even if we didn't have the following line, the CUDA get last error call would capture our asynchronous errors. Okay, and so this is another way, if you don't want to use your own debug macro, this is another way to get nice localization of kernel errors to the kernel launch that caused them. Okay, let's talk about another characteristic of these synchronous versus asynchronous errors. These errors occurring as a result of the general use of the CUDA runtime API versus errors that occur as a result of kernel device code execution. So these two different types of errors, which I have referred to as synchronous and asynchronous, have other names that distinguish them. Another way that you'll sometimes hear people refer to those errors is sticky versus non-sticky. What do we mean by that? Well, this pertains to the way the CUDA runtime behaves in the presence of these two kinds of errors. If we have a non-sticky error, that would also be referred to as a synchronous error in my previous terminology. In other words, that's something detectable by the CUDA runtime as a result of a CUDA runtime API call. It's also detectable at the point of kernel launch before the kernel has actually begun to execute. Those would be synchronous errors. We could also refer to those as non-sticky errors, and we could also refer to those as errors that do not corrupt the CUDA context. These are all roughly the same thing. And what they mean is that this error will allow you to continue. So for example, if I do a CUDA malloc call and I simply have a parameter that's way out of range, whatever that number is, I don't have that many bytes available in device memory. That CUDA malloc call is going to return some sort of out of memory error. However, if I did another CUDA malloc call after that, or really any other activity of the runtime API, like launch a kernel or what have you, we would expect those to behave normally. In other words, if the subsequent CUDA malloc call was for an appropriate amount of memory that was available, we would expect it to succeed and that memory would be actually allocated. However, that is characteristic of a non-sticky error. And we say that the CUDA runtime is allowing us to proceed because that particular error has not corrupted the CUDA context. And so in other respects, we observe what we consider to be normal behavior by the CUDA runtime. However, these kernel execution asynchronous errors that I've been talking about are sticky errors. And that means a couple things. First of all, it means that the CUDA runtime API is essentially no longer usable in that process. It is completely broken. There's nothing you can do at that point. If you attempt to do additional subsequent CUDA runtime API calls anyway, they will all return the same error. What are some examples of those errors? Some examples of those errors might be things like kernel timeout. So the kernel was running and then there was some sort of timeout mechanism that caused the kernel to terminate. Another thing might be an illegal instruction. So the instruction pointer in one of the CUDA threads, was advanced and settled on something that was not a valid instruction. Another would be a misaligned address. Another would be an invalid address. In fact, invalid address might be one of the most common ones. And this means that you simply access something out of bounds. You accessed an array beyond the end of the array or what have you, or you dereferenced a null pointer or something along those lines. You'll get an invalid address. Those types of errors that all are associated with kernel device code execution will cause what's referred to as a sticky error. They will corrupt the CUDA context, and the CUDA runtime API is no longer usable in that process. Okay, and if you attempt to use it anyway, you're going to get the same error. So every single API call after that point will return the same invalid address error, even though it has nothing to do with that CUDA runtime API call. Generally speaking, the only way that you can recover from a sticky error or a corrupted CUDA context is to terminate the owning host process. In other words, end the application. However, this is sort of getting off in the weeds, so I'm not suggesting this is particularly important, but if this is something that's extremely problematic for you, it is possible to design a multi-process application that spawns child processes that use CUDA. And then if the child process runs into an error, like a sticky error, like what we're talking about, you can terminate that child process, essentially revert to the parent process, and the parent process can then spin up a new process that will start over, so to speak. It won't have any of the context or state left over from the previous process, but it doesn't necessarily require the end or termination of the application as a whole if it's a multi-process application. And there's a link there that you can use to discover more about that if you would like. That's very much a minor topic or point. So what I'd like to do now, I'm getting towards the end of my error checking section. What I'd like to do now is talk about some examples, and then I'm going to pause for a moment in a few minutes and see if there are any questions. So let's imagine that in my host code, I set a variable called shared mem size equal to 32,768. We're going to use this as a variable to specify the amount of dynamically allocated shared memory, which is one of our parameters for a kernel launch, one of those parameters inside the triple chevron syntax. And when I was writing this code, I said, oh, I need 32,768 bytes. And that's okay, because we know from our knowledge of shared memory that I can actually allocate up to 48 bytes for a single thread block, and that will work on any GPU without any special handling. But then I was writing my kernel code and I forgot that I had already sized it by bytes, so I mistakenly multiplied by that variable times size of double. And that isn't what I had intended to do. And if size of double is 8, so 8 times 32,768 is 256 bytes. And if I'm not mistaken, 256 bytes won't work on any CUDA GPU. That you can't ask for that much shared memory. So that's discoverable at kernel launch time. That would be an example of a synchronous error associated with the kernel launch. And if we do CUDA get last error after the kernel launch, as you were instructed, it will report the error associated with an invalid parameter, basically, is the error you're going to get in that case. And it will clear that error if it's not sticky. So this is definitely an example of a non-sticky error. This is a synchronous error. And it will clear that error, which what clearing it means, if I did another CUDA get last error, for example, right after that one that reported the invalid parameter, the next call to CUDA get last error would report CUDA success. We have another API call to be aware of called CUDA peak at last error. And peak at last error is just like CUDA get last error, except it doesn't clear it. So I could do CUDA peak at last error and I would see invalid parameter. And if I did it again, I would see invalid parameter. And if I did it again, I would see invalid parameter. Then if I did CUDA get last error, I'd see invalid parameter. Then if I did CUDA peak at last error, I'd see CUDA success, because the CUDA get last error cleared out the synchronous non-sticky error from the reporting mechanism. Here's another example of a synchronous error that you could have. In this case, I had intended to copy data from host to device, or let's say it doesn't matter. I could say I intended to copy data from device to host, and I got my sense of pointers reversed. So my first pointer in CUDA memcopy is the destination pointer, and let's pretend that was a device pointer. The second pointer is the source pointer, and let's pretend that was a pointer allocated in host memory, and then the size parameter. And now we have the token CUDA memcopy device to host, and that doesn't match the sense of these pointers. The sense of these pointers is suggesting that we want to copy from host to device. That would be a synchronous error, okay? Now, if I just issued the call that way, which is what you might do if you were using sloppy error checking or no error checking, that error, the error associated with the inappropriate orientation of the pointers in the CUDA memcopy statement would be reported if I captured that. But if I did a subsequent call, just as you see here, okay, if I did a subsequent call and I did look at the error checking, so the first thing I do is the second to last CUDA memcopy operation, and then I do another CUDA memcopy operation, and now my sense of pointers is correct, okay, because it matches the host to device token. The ret value on the second call will return CUDA success, because that is the error that was associated with that runtime API call. In a sense, the error that was associated with the previous call that I did not capture explicitly is in a sense lost. Okay, so this can be very confusing, and this is why I suggest doing rigorous error check. One of the reasons why I suggest doing rigorous error checking anytime you're having trouble with a CUDA code. Now, if I did CUDA get last error after the end of all this, it would still report the invalid parameter on the CUDA mem copy that had the broken orientation. So as you've discovered, there's a little bit of complexity here. And so one of the things that people will often do is build macros that capture or that do all the things that they would typically want to do when they have the necessity to capture a CUDA error, a CUDA runtime API error. And so there's a million ways to skin the cat. This is not the only way to do it, but I'm just giving you an example of a macro that I have used many times in the past. And this type of macro is something that you would typically drop into your code after the runtime API call. So every time you do a runtime API call, just drop this macro in there. Okay. In other words, use that first line, CUDA check errors with an appropriate message string. Okay. This is not the only way to do it. You'll see many people who build macros that actually wrap the call itself, and so they handle the error directly instead of using CUDA get last error. Again, there's a million ways to skin the cat. The most important thing to do is to do the rigorous error checking. It doesn't matter that much whether you like to do it one way or the other. One of the things that I will say that I consider macros to be useful is that it's very often very useful when you're debugging a big application to have the error associated with a particular line in a particular file. And a macro does a good job of that because the macro will be expanded at the point of usage. Okay. If instead you have an ordinary C or C++ style function call to handle the error, even if you put this file and line stuff in the function call, it's simply going to report the file and line where that function is defined. And that's useless, basically. Okay. So the macro has that benefit, in my opinion. All right. So we are now done with the basic treatment of CUDA error codes. And I want to take a quick look at the chat and see if there are questions. Okay, I'm sorry that this training conflicted with another event. However, it's being recorded, so hopefully you'll have an opportunity to review it later if you need to, or anyone who wasn't able to attend. Doesn't look like there's any other questions in the chat that I can see, so I'm going to continue.
Bob, sorry,
yes,
can I just ask a question? This is Tom, Papa Theodore Oak Ridge. Can you go back to slide 8?
Yep. Just a second. 8.
So here you said that those bottom 2 bullets, CUDA mem copy, right? And you get a, if you would have checked that, right, you would have got a error that told you that,
yep.
Yeah. And then at the bottom part, you said if you called that right afterward, it would return success. Why is it that calling a API call and getting a return from it after a kernel launch doesn't clear out or doesn't replace the error the way that this sort of replaces it and shows success? I mean, I understand it's different, that it's asynchronous, but what is the reason for that?
Okay, I'm not sure I followed. When in this particular example, for the last 2 lines of code here, there's an error associated with the second to last line, okay? And there is no error based on the syntax of the last line. And so what I said was the ret value on the last line would contain CUDA success. And it does not contain error associated with the previous CUDA mem copy. And the reason for that is because those are synchronous errors, and the ability of an error code to be reported asynchronously is dependent on that error being asynchronous. So synchronous errors, even if they have previously existed, do not get reported by subsequent CUDA runtime API calls, except for CUDA get last error and CUDA peek get last error. But asynchronous errors can be reported by any CUDA runtime API call. So now you're asking about a kernel launch, and that's where I lost the thread. So if you could pick up at that.
Yeah, so the question would be, if the second to last bullet point, there was a kernel launch instead, it would return an asynchronous error. And I think that's the answer, is that if that second to last bullet point was a kernel launch, it had an error, and then you call the API call right afterward, it wouldn't
Let's drill into
overwrite.
that. Let's drill into that. Let's
Sure.
talk about that, because that's a good question, and it helps to reinforce the idea of synchronous versus asynchronous errors. So we talked about the idea that a kernel launch could have associated with it either a synchronous error or an asynchronous error, and we know that those two have somewhat different behavior. Let's suppose that instead of the second last line of code here being a CUDA memcopy, it was the kernel launch, and it was the kernel launch that you see at the top of this slide. In other words, it has a problem in the shared memory size. Okay, so it's going to fail, and it's going to fail with a synchronous error. If I did that kernel launch, the K kernel you see at the top of the slide, as the second last line, and then I did the ret equals CUDA memcopy, the last line, that would also not report the synchronous error associated with the kernel launch. Okay, again, this is I don't know if I should apologize, but this is just confusing, and you really have to either have an intimate understanding of all this stuff or just be rigorous about mechanically doing error trapping. Okay, and so what I'm trying to suggest is that you rigorously trap errors and use a mechanical process. Like every time I do a CUDA runtime API call, I'm going to wrap it in a macro. Every time I do a CUDA runtime API call, I'm going to follow it up with another line that's effectively a macro. Every time I do a kernel launch, I'm going to do a CUDA get last error, whether that's in a macro or not. And if I need to debug this code, I'm going to have a mechanism to force those kernel launches to be quote unquote synchronous. In other words, blocking. Synchronous with respect to the host thread, blocking. Okay, that's 3 or 4 suggestions that I just gave you there that I'm going to define as the mechanical method to deal with this without understanding all the nuances of when will a synchronous error be reported, when will an asynchronous error be reported. I don't mind trying to explain all that, but if that seems challenging to understand that a kernel launch where the CUDA memcopy line is, the synchronous error would not be reported on the next line, but an asynchronous error might be reported on the next line. It's just weird, I'll give you that. Okay, but it's just the nature of the definitions that were set up for error reporting. And if you stick to a trusted mechanical process for error confinement, you're not going to have to worry about the detailed mechanics. That's my suggestion.
Okay, fair enough. Thanks.
Okay. So we're going to continue now with our next topic, which is, as I mentioned, a tool. So the tool is called Compute Sanitizer. And Compute Sanitizer is a functional correctness checking tool. It's installed with the CUDA toolkit, so it should generally be just, if you have proper, paths and whatnot set up so that you can use NVCC, for example, then you should also be able to access Compute Sanitizer without doing anything special. It's a tool that is a runtime functional correctness checking tool. That means you're going to use it at runtime, and you're going to have it effectively run your application for you, and you're going to it's going to run your application in an instrumented way. So it's going to run your application using special control over the behavior of the application and doing lots of things that would not ordinarily happen, so that it can provide additional information about the behavior of your application. So one of those things that would not ordinarily happen is that it provides automatic runtime API error checking. So even if your code doesn't trap any errors at all, you're not doing rigorous error checking, you're not doing proper CUDA error checking, if you run your code under Compute Sanitizer, any API error will be reported by Compute Sanitizer. Okay, so this by itself, if you're at like an IT help desk, or if you're in HPC development engineering and you're helping other people with their codes, and they may have been sloppy when they wrote their code, tell them to run it under Compute Sanitizer, because even if they were sloppy with their API error checking, if they have any problems at all, synchronous or asynchronous, kernel launch or CUDA runtime API calls, Compute Sanitizer will report every single one of those. Okay, so that's a useful feature all by itself. But of course, it does a lot more than that. It can work with essentially no matter how your code was built. Okay, so if your code was built using CUDA Fortran, that's okay. If it was built using CUDA C++, that's okay. If you were using some flavor of Python like Numba or CuPy or something like that, that's okay too. Compute Sanitizer will do the same thing. Now, if you're using some intermediate construct like CuPy or Numba, some of the symbols that Compute Sanitizer uses to report what's going on might be a little bit confusing. But nevertheless, the fact that it reports a runtime API error or a kernel launch or kernel execution error is extremely useful. Compute Sanitizer is a tool that has multiple subtools. The default tool will refer to that as the mem checker or the memcheck tool. And this detects all the things that we've talked about so far, like runtime API error checking. And it also detects illegal code activity in device code. So illegal instructions, illegal memory access, misaligned access, things of that nature. It will capture those and report those with some detail, right? If you capture that and if you catch that using a CUDA runtime API call, like CUDA device synchronize, you may simply get some sort of nondescript error, like an error code 700, which is execution failure or something like that. But this is going to give you more detail into what's going on. And in fact, in a moment, we're going to see how you can get even a lot more detail from this tool. This is a very valuable tool. So we're unpacking its feature set. The memcheck tool is where you're always going to start. Always do that first. That's the default tool, which means you don't have to specify an additional command line parameter to get the memchecker. It has 3 additional tools that we'll talk about called race check, init check, and sync check. All of these require specific command line switches in order to get this functionality engaged. Okay, so the race check tool detects shared memory race conditions. Let me repeat that, shared memory. It will not detect a race condition associated with global memory. Okay, you can certainly have a race condition associated with global memory. This will not detect it. But shared memory is where people often get tripped up with races between threads. And so this tool is very useful for capturing those types of problems. Those types of problems don't generally manifest themselves in a way that the mem checker would catch. They don't represent illegal access. The code didn't do anything illegal, but you have a race condition and therefore you're not getting the results you expect. And in fact, race check can detect a few different kinds of race conditions: read after write, write after write, write after read. The init check tool detects accesses to global memory where the global memory has not been initialized. Okay, it might have been allocated. You might have done a CUDA malloc call, and so the code is legal in that it's touching a properly allocated piece of memory, but nothing has initialized that memory to 0 or whatever the appropriate initialization value is. And that's almost certainly, if you're reading something like that and using it in your calculations, that's almost certainly a coding error. You've almost certainly made a mistake if you're doing that. And so this tool can detect that. And the last subtool is sync check, which detects illegal use of synchronization primitives. The primary synchronization primitives we would have in focus here are things like sync threads. After CUDA 9, we also learned that there are some additional primitives called sync warp and the things that are associated with the .sync method associated with cooperative groups. These are all examples of synchronization primitives, and sync check presumably or ostensibly has or oversight on illegal use of those. This is a complicated tool. I suggest that you refer to the documentation. Okay, this is by no means a complete treatment of Compute Sanitizer, but I just want to get you to the point where you believe it's valuable and so that you use it regularly when you're having trouble with your CUDA code. In fact, I would suggest that you not even let the idea that your code might be correct enter into your mind until you've run this tool on it. Okay, even if it's giving you the right answer, I wouldn't personally trust any code that I wrote unless I ran Compute Sanitizer on it. Then I would start to believe that, yeah, maybe this is bulletproof code. Okay, so we'll start with the memcheck subtool. It's the default tool. You could sort of think of this tool as being something like Valgrind if you're familiar with that from a host code uses perspective. If you're not, that's okay. Don't worry about that. The basic usage is just as you see here. Again, the tool will be available if you have proper paths set up. So if you can access NVCC, you can access Compute Sanitizer, just as the way you have here. And you just, when you're starting out, you just give it the name of your executable to run. This will, in addition to detect API errors that we talked about, it will also detect things that might not be detectable ordinarily. For example, invalid or out of bounds memory access. Now, you might think that's obvious, but in fact, the runtime by itself, without additional help from a tool like Compute Sanitizer, will not always tell you that an out of bounds memory access has occurred. Okay, And there's a number of reasons for this. It has to do with the overhead associated with that and allocation granularity and things like that. But the bottom line is, if I allocate an array of size 10 and try to access element number 11, which is illegal in C or C++, the runtime is almost certainly not going to flag that as an error. So if I don't use a tool like Compute Sanitizer, I may not know that that sort of error is lurking in my code. These other types of errors, invalid program counter, invalid instruction, misaligned address, those are typically things that will be trapped by the runtime. So they would result in an error like error 700 or 719 or something like that without any additional help from CUDA memcheck. Now, here's one of the real gems of CUDA memcheck, and that is that if you add the line info switch, just as you see here, when you're compiling your code, CUDA memcheck will not only tell you that you had an invalid or out of bounds memory access in a particular kernel, it will also tell you the line of source code that triggered that error. That is remarkably useful, okay? In addition, this switch dash line info is useful with other tools, like, for example, Nsight Compute, which we're not here to talk about today. But if you were doing profiling, it's very useful and convenient to have source level information in the profiler, and Nsight Compute can give you source level information in the profiler if you compile your code with dash line info. So you might want to just get in the habit. There's not really any downsides that I know of. Maybe there's some code bloat. I'm not really sure there is. But you may want to just get in the habit of always compiling your codes with line info. It'll be useful if you run CUDA memcheck. It'll be useful if you do the profilers. Another thing to know about the memcheck tool or the Compute Sanitizer tool, let's say, is that generally speaking, it's going to have a performance impact on the speed of kernel execution. Your code will probably run a lot slower, like 10 times slower, okay? And the reason for this is because it doesn't have hardware mechanisms to trap all this. If we had hardware mechanisms in the GPU that did every one of these things, we wouldn't need Compute Sanitizer. We could just have runtime API error checking and we'd get all this information. We'd just yank it out of the hardware. But we don't have support for all of this capability in hardware. And so the tool has to do some software instrumentation of your code in order to make all of this work. And that can slow it down a lot, okay, a lot. It's not uncommon to see 10x slowdown in the speed of kernel execution. So obviously you need to think about that. And if you're going to run this on a huge application, it might cause that huge application to take a lot more time. Also, if you have the opportunity or the ability to do unit testing on your code, breaking your code into pieces and testing individual pieces, that's a really good way to use this tool as well, because that's going to cut down the scope and make things run quicker all by itself. There's other features that we won't really cover in this session. It has the ability to do leak checking for device side memory allocation and free. This is in kernel use of new or malloc. And if you have leaks associated with that, a new that doesn't have a corresponding delete, a malloc that doesn't have a corresponding free. Again, this is all in device code now. It can do leak checking on that. Also, as I've mentioned already, the error checking is tighter in some cases than ordinary runtime error checking for the reasons that we talked about, right? So if you have an allocation and you're accessing element 11 of an allocation that goes up to 10, this tool will catch it and the runtime won't, pretty much guaranteed. So here's an example. And what I'd like to do is pretty much focus on the right-hand side because there's a lot of useful information in here, okay? And so you can see on the left-hand side, I have a very simple kernel where I've allocated a variable D that I passed to the kernel call, and that variable has 42 bytes associated with it. And I'm trying to access what amounts to the 44th byte, okay? 43 here, starting with 0 means the 44th byte. That's illegal. Can't do that in C or C++. If I ran this code without Compute Sanitizer, like you see on the left-hand side, it just runs, okay? You don't get any indication that anything is problematic at all. And even if we trapped the CUDA device synchronize call at the end of the kernel, which ordinarily would catch kernel execution errors, you're not going to see an error, okay? However, if I run this code with Compute Sanitizer, we get the output on the right. Now, the output on the right has been excerpted and also cut down a little bit for space, but the important stuff is here. First of all, it's going to tell us that I have an invalid global write. So global means I'm writing to global memory. If it said shared there, I would know that the shared indicated that I'm writing to shared memory. The fact that it's a write, not a read, is useful, okay? And it's of size 1 byte. And it's happening at line 2 in my kernel code. How do we know it's happening at line 2? Well, you can see it's calling out the file name, home user2 miss t1866.cu, :2. That :2 means it's happening on line 2. And line 2 in this case corresponds to D of 43 equals 0. That's exactly where the error occurred, okay? There's other information here. It's telling you which thread and which block caused this error. There's some backtrace information that I'm not going to spend any time on. And then as we get to the bottom, we'll see that we're now reporting an error 719 on the CUDA API call to CUDA device synchronize. So this error 719 is a runtime kernel execution error, unspecified launch failure, okay, which means that the kernel did something in execution that it wasn't supposed to do, but we're not giving you the specifics. And this is curious because I just said if I did error checking on that CUDA device synchronize call on the left-hand side and ran the application normally, it wouldn't report an error. And now we see that, first of all, Compute Sanitizer does trap error returns from CUDA runtime API calls, and it is reporting an error. So what's going on? Well, what's going on is the runtime behavior is different when Compute Sanitizer is in control. On the left-hand side, there was no error detected. On the right-hand side, there was an error detected in the kernel launch. And so in addition to reporting that kernel launch error, just like it does with every other CUDA runtime API call, it reports any errors returned from that call. So we're seeing there that it's reporting the error associated with the CUDA device synchronize call. And that report specifically occurred because we were running it under Compute Sanitizer. Okay, let's go on. Let's talk about the race check tool. So the race check tool is used, as we talked about, to detect shared memory race conditions. And it's important for us to remember or remind ourselves that CUDA specifies no order of execution among threads. Now, you can impose order with things like sync threads, but if you don't use explicit mechanisms, CUDA specifies no order of executions. One thread can race ahead of another, okay? Shared memory is commonly used for inter-thread communication. And so if we have threads moving at different speeds, if you will, through the code, at different rates through the code, then it's possible that I might think that I'm going to read something out of shared memory because some other thread wrote it already, but that thread hasn't gotten to the point where it was going to write to shared memory. And so when I read shared memory, I get bogus values, okay? And so in this scenario, when we're talking about loading and unloading data from shared memory, especially when we have inter-thread communication, ordering of reads and writes matters for correctness. Doesn't mean that it's illegal. It just means you won't get the correct answer. And so in order to use the race check tool, we're going to execute it like this. We're going to say --tool race check and give it our application to run. And it will find 3 different kinds of errors: write after write, read after write, and write after read. In the interest of time, I don't want to spend a lot of time talking about these because the concept of a write after write, read after write, or write after read error, a race condition error, is not unique or specific to CUDA. So you can learn more about this in, yourself just by studying it. But let's use the example I just gave. One thread is writing a value. Another thread is reading the value. And the only way this is correct is if the read occurs after the write. So this would be an RAW hazard. And what that means is that if I did not force the read to wait until the write had occurred, I might not get the correct answer. How do I force it? With intervening synchronization. So I have threads write to shared memory, and then before the communication occurs, transfer to another thread, I have something like sync threads or sync warp. Then I know that the write occurred before the read. And in that scenario, if I had proper synchronization, no race condition or hazard would be reported. That's just one example. WAR and WAW are 2 other types of mechanisms, but hopefully you can imagine what those might be like. You can get more detailed reporting if you want. In other words, I'm going to cover the basic reporting that you get based on the syntax that I'm showing on this slide, but you can get much more detailed reporting on these errors if you want. Okay. So here's an example where we have a shared memory race. This code is designed to reverse bytes. So if I write the bytes 0, 1, 2, 3, 4, 5, then when they're reversed in global memory, they're going to appear as 5, 4, 3, 2, 1, 0, or something like that. Okay, so this is simply loading up. Each thread is loading up shared memory with a value from global memory, and then when we write back to global memory, we simply reverse the order of indexing that we use to index into shared memory. Now, this means that a particular thread that's reading a value out of shared memory typically did not write that value. Therefore, the line of code that says s of thread idx.x equals d must occur for all threads before d equals s occurs for correctness. Okay, and we are obviously missing any synchronization in between those two. And so we would get an error, as you see on the right-hand side. In this case, it's the simple kind of error reporting. So it's a race reported between a write access at line 4 is the way to read that, and a read access at line 5 in my reverse kernel. Okay, so now it's focusing my attention. Obviously, in this kernel, it's so trivially simple that I don't really need that help. But a more complex kernel, that's very useful to know, not only is this a RAW hazard, but this hazard specifically is associated with lines 4 and 5, the write occurring at 4, the read occurring at 5. So that's very useful information when you're trying to sort this out. And you can get even more involved reporting than that if you would like. Encourage you to read the manual. Notice that there's no other errors reported. The code didn't do anything illegal, okay? All right. The init check tool, as I mentioned, detects the use of uninitialized device global memory. There's really not a lot of complexity with this. It's exactly what it describes, so I don't need a slide to walk through its behavior. And on the left-hand side, we see an example of a code that does exactly this. It's simply copying things from location in to location out. And so I did a CUDA malloc on my in location, that's D1, and my out location, that's D2. But I never initialized anything that's associated with the D1 pointer. I simply ran the kernel and copied from in to out. And so the init check tool, when I run it, as you see on the right-hand side, will report a problem with that usage. Okay, and specifically it's in line 3. Again, this isn't, this kernel is so trivially simple, I don't need that help. But in a complex kernel, knowing that it occurs on line 3 could be very useful for me being very productive in finding out where the problem is. Okay, and this again is excerpted output. There would be more output that would report a whole bunch of errors of the same type, and it would collapse those all into a single error. So it would report additional examples of uninitialized global memory read, all associated with the same line of code. Okay, let's continue to our last tool, the sync check tool. And in the case of the sync check tool, it applies to usage of sync threads, sync warp, and the cooperative groups equivalents like this group.sync, or the usage of the .sync method. Typical usage is for detection of illegal use of synchronization. Not all necessary threads can reach the sync point. The sync point being either sync thread, sync warp, or this group.sync. And this could be something that happens either at the thread block level or the warp level. So it typically would involve some sort of conditional code, okay? Conditional code that prevents all of the threads from reaching a sync point appropriately. Now, this tool, if you're running on a GPU that's prior to the Volta architecture, it does pretty much what you think it should do. So if I had a construct that said if thread IDX equals 0, and then I did sync warp or sync threads in that body of that if statement, that would be illegal because you're preventing other threads from reaching that with that conditional code. However, when we introduced the independent thread scheduling feature of Volta and beyond, compute capability 7.0 and beyond, this sort of illegal character became relaxed. In other words, it is now legal in CUDA to have threads that are excluded from participating in a sync warp or sync thread where you think they ordinarily should, as long as those threads have some other characteristics. And basically the other characteristic is those threads have to exit. Okay, so if those threads exit instead of participating, that is now legal usage of sync warp and sync threads. And this is at a minimum, somewhat counterintuitive. And it also limits the usability of this tool, because there are many situations that we might have thought were illegal and are no longer illegal. And so I'm not going to spend a lot of time on this particular tool, but I would encourage you to read the documentation if you'd like to see an example of proper usage of this tool or an example of valid usage of this tool on Compute Capability 7.0. I would encourage you to read the docs. If you want to try using this tool, you can invoke it just as you see here. Okay, I mentioned that this session was going to run long, and so I hope you'll be able to stay with me because I think our next session is going to be very useful. Before I do that, let me take a quick look at the chat. And we do have some questions, it looks like, or at least one question. How does the Compute Sanitizer compare with Valgrind in terms of time needed? Well, Valgrind is a host code checker, and host code, one of the things, Valgrind can do a lot of things, but one of the things that it can do is detect illegal memory access. So just the same kinds of ones that I described. For instance, I allocated an array of size 10, and I access element 11, that's illegal. Valgrind will catch that. Ordinary CPU host code probably wouldn't, might not anyway. Another thing that Valgrind can do is detect leaks and other things as well. I don't want to try and give a tutorial on Valgrind. I'm not an expert on Valgrind, and I don't really know how Compute Sanitizer would compare with Valgrind because they're really doing two different things, okay? Compute Sanitizer is largely focused on your usage of the CUDA runtime API and device kernel code execution. Whereas Valgrind is focused on host code. So Valgrind can detect illegal usage of host code, kind of like what I described. If you use Compute Sanitizer, it has no facility to detect that kind of ordinary illegal usage of host code. So you really will need probably to run them both. Regarding speed, I mentioned that I've already mentioned a few times now that Compute Sanitizer can easily slow down the rate of device code execution by 10x or more. So if your code execution is dominated by kernel device code execution, I wouldn't be surprised to see a 10x slowdown. And there might be some pathological scenarios where you could see something like 100x. I don't know that I've ever witnessed that, but I've witnessed 10x frequently. How is Compute Sanitizer different than CUDA Memcheck? That's a good question. CUDA Memcheck is a tool that on the surface appears to be nearly identical. The main difference is that CUDA Memcheck is designed to be used on GPUs up through approximately the Volta generation, so Compute Capability 7.0, and Compute Sanitizer is basically being sunsetted. Sorry, CUDA Memcheck is basically being sunsetted, which means that CUDA Memcheck is not the proper validity checking tool, for example, on a Turing device or an Ampere device or any future GPUs. We have a little bit of overlap on a Volta GPU. You can use CUDA Memcheck or Compute Sanitizer, and from a syntax standpoint and a behavior standpoint, they're nearly identical, okay? So the key difference is, as you move forward in your CUDA journey on newer GPUs, you will want to use Compute Sanitizer. That's why we're presenting it here. Yes, CUDA Memcheck will soon be deprecated. That's correct. It's going to be deprecated at approximately the rate at which we deprecate GPUs. So CUDA Memcheck will probably stay around at least through the end of life of Volta, because it's a valid, in other words, supported tool on Volta. Okay. It's not my purpose here to give future-looking statements, so I'm just giving you that as my impression or what I would anticipate, what I would expect. I'm not making a guaranteed statement that it will or won't be deprecated. I'm not making a guaranteed statement that this is exactly the schedule upon which it will be deprecated. I'm saying my expectation is that the tool will be kept around as long as there exists supported GPUs of Compute Capability 7.0 that are supported by the current CUDA toolkit. But it still doesn't mean that you would want to use CUDA Memcheck on a Turing device. You wouldn't, ever. Okay, let's continue. Yes, there probably are new features in Compute Sanitizer. There's both tools are way more complicated than what I've described here. So if you want a laundry list of all the feature differences, you're going to have to go to the documentation for that. As far as what I've described here, the behavior of the tools are nearly identical on Volta. Okay, let's switch gears now and talk to actual debugging. Now, when we start to talk about actual debugging, I'm going to suggest that it's one of my least favorite activities. I have to get out, I have to dust off a tool that I don't use all the time. And I have to think carefully about the way this code is supposed to work and lots of other things that I might not ordinarily be thinking about. The previous tools that we've talked about do all that thinking for you. So I would encourage you, before you dust off the debugger, to use proper CUDA error checking and run your codes with Compute Sanitizer. All right, let's continue now with debugging. Okay, so CUDA GDB is a tool. It is based on the widely used GDB debugging tool, which is part of the GNU tool chain, so the same place that GCC and G++ come from. This is not intended to be a tutorial on GDB. However, two things. I'm going to give you a run through of how to use CUDA GDB, which about 90% of it is simply how to use GDB. Okay. And later on in this presentation, let me just advance a few slides here because we're almost at the end of my slide deck. Okay. I'm going to cover everything up to this point. However, I've got some backup stuff that covers CUDA GDB, covers GDB basic syntax. And so this basic syntax on these backup slides will be available to you if you look at the slides, just 2 slides. And it will cover essentially all of the command line usage that I'm going to demonstrate during the demo. Okay, so I'm not going to go through these slides. I will go through them in the form of a demo soon. Okay. So CUDA GDB is a command line debugger. It's not a graphical debugger. That'll become obvious in a moment. It's used for typical operations like setting breakpoints, single stepping, inspection of data, and a few others. If you know how to set breakpoints, single step, inspect data, and maybe 1 or 2 other things, you have about 99% of the capability that you need to debug any code. Okay. CUDA GDB uses the same command syntax where possible as GDB, and it does provide certain command extensions. Those command extensions typically have the word CUDA in the command name, so it's pretty obvious that you're using a command extension. Generally, you want to build debug code when you're using a debugger. That's not a CUDA specific statement. So if you're building host code and you want to do some debugging on it, you're generally going to want to build debug host code. And if you were using GCC or G++ for that, you'd add the -G, little g switch, and that would build debug code for you. We're going to focus here on debugging device code. However, the mechanics of it, setting breakpoints, single stepping, and inspection of data, are essentially identical to the way that you would set a breakpoint in host code, single step in host code, and inspect data in host code. So there's really not a lot here that's actually going to be CUDA specific. But we will eventually, I will cover some ideas that you will want to know when you're debugging device code, particularly in the area of debugging a massively thread parallel application. That's something that you may not have had a lot of experience with, and it's something that you definitely want to have a few brain cells reserved to go, aha, this may be something to do with this parallel thread model that I'm working in. It does support debug of both C++ and CUDA Fortran applications. However, there are some limitations with CUDA Fortran. I think I will mention those later. When we want to get started to debug code, the first thing we need to do is build debug code. And as I've mentioned, the -g switch is the standard GNU switch for building a debug host code. And it is the same switch that you would use with NVCC as well to do the same thing. In other words, to build debug host code. Okay. If you want to also build debug device code, in addition to the -g switch, you would specify the -big G switch. Okay. So typically, when you're getting started to do debugging with NVCC, you'll specify both of those. Okay. This does a variety of things. It makes necessary symbol information available to the debugger so that you can do source level debugging. And we'll see what source level debugging means in just a moment when I go through the walkthrough. But it has to do with the fact that we can reference lines of source code and we can move through our code as if we were moving through our source code, even though the underlying machine is really not doing anything at all like executing lines of source code. It's executing the compiled code, which is quite a bit different. The -G switch, another thing to be aware of is the -G switch has a substantial impact on device code generation. It changes the device code that's actually running, okay? Almost guaranteed. It's going to remove most optimizations. And as a result of moving most optimizations, I suggest that you use this for debug purposes only. Stated another way, don't do performance analysis on device code built with the -G switch. It is not going to be reflective. 99% of the time, it's not going to be reflective of the performance of that code if you had built it without the -G switch. You should, in my opinion, you would never deliver production code that's compiled with -G. Okay, if you see it differently, then you're welcome to do whatever you like. As a result of the fact that the code construction has changed and most optimizations are disabled, the -G switch will often make your code run slower, potentially a lot slower. Okay. In rare cases, this is of course not desirable, it's not intended, but in rare cases, the -G switch may change the behavior of your code. It typically doesn't mean illegal things no longer become illegal or something like that, but it could mean a race condition is less evident. So that's a bit problematic if something like that were to occur, but nevertheless, it is a debugger that you can use, and it's going to be a good starting point for you anyway. So I think it's rare when you would expect a significant behavioral change like that, but it does happen. You can certainly find reports of the so-called Heisenberg bugs, where when I tried to debug it, the bug disappeared. And maybe one of the things that I did when I tried to debug it is I built debug code, and then when I write my debug code, my application appears to run correctly. So how do I debug it if it's running correctly? That's a problem, but I'm going to suggest to you that it's rare. Make sure your code is compiled for the correct target. The reason for this is because, as I mentioned, when we're building device code, there's a compilation process going on, and we would like a tight association between the device code and the source code that was used to generate that device code. So it's really important to make sure that you're specifying a target so that you have actual SAS code that you're debugging. Okay, some additional suggestions for preparation. Now, these are sort of less mandatory. If possible, make sure your code runs correctly under Compute Sanitizer. Now, if it doesn't run correctly, that might be the reason you're dusting off the debugger, okay? But in many cases, we use the debugger to find out why my application is not producing the correct answer, as opposed to finding out why my application is seg faulting or producing illegal memory access. You have, in my opinion, better and more powerful tools to localize those kinds of errors. I suggest you use those, and use those tools to get rid of things like illegal memory access. You don't have to. You can still debug code that way, but I'm going to suggest that you're going to be more productive if you use the tools that are abstracted to a higher level, like Compute Sanitizer. It's also convenient to make sure your host code is sane. In other words, it doesn't seg fault. Some people like to debug seg faults with the debugger. That's not my approach, but you can do it that way. If that's the case, then do whatever you like there. If possible, make sure your kernels are actually being launched. Sometimes people say my code isn't producing the correct results, and the reason it's not producing the correct results is because the kernel isn't being launched. And the kernel isn't being launched because I did something like I gave it an invalid config parameter and I didn't do proper CUDA error checking. So I had no idea that the kernel wasn't actually being launched. But I do know that it's not giving me the right results. And so rather than having a knee-jerk reaction to say dust off the debugger, it's going to be confusing if you dust off the debugger, because if you set a breakpoint in a kernel that never gets launched, you're never going to hit that breakpoint. That's going to be confusing. Okay, so I'm just trying to save you some time here. There's a number of different ways that you can validate that kernels are being launched. A quick and easy way to do that is with the profiler. The profiler will list every single kernel launch in your application. And if you miss something or there are no kernels launched, that's a good indication that maybe you should think about taking another look at your host code before you start to try and debug device code. Okay. As I mentioned, most of what we're going to cover is GDB specific, but not CUDA GDB specific. Okay, so I'm mostly teaching you how to use GDB here in just a moment. However, there are some CUDA specific extensions to GDB, and I want you to be aware of those because we're actually going to use one or two of them. The first one is the set command. Now, the set command is part of GDB, but when you say set CUDA, now you're setting parameters that are associated with CUDA behavior, okay? And so one of those is launch blocking on off. So if you set CUDA launch blocking on, that means that every kernel is now synchronous. When I say synchronous, I mean it's as if a CUDA device synchronize was in place right after the kernel launch in host code, okay? And so the launch effectively pauses the host thread, and that might be useful. You can also have it break on launch. Every time a kernel is launched, you will automatically hit a breakpoint on the first line of code. And there's other things that you can do with set CUDA. We won't actually be using that during our debug sessions, but those might save time a little bit. Info CUDA, info again is a GDB command, but when you say info CUDA, it's now something that's specific to CUDA GDB. And this allows you to get general information on system configuration, like, for example, what devices are in my system. So I can say info CUDA devices, and it will show me what devices are in my system. And I'll try to remember to demonstrate that in just a moment. And there's other things that you can ask in the info CUDA command. Again, I'm moving quickly in the interest of time. This is not intended to be a complete tutorial on either GDB or CUDA GDB. There is documentation available. I'm trying to cover what I think are the most important highlights. The last command is obviously a CUDA specific command because it just starts out with CUDA. And the primary purpose of this command is used to inspect or set the current focus. What this means is you should be aware that you are now stepping into debugging in a massively thread parallel environment. Okay, this means that typical debugger mentality, usage, and behavior, like what you'd expect in GDB, only applies to a single thread. What about all the other threads? Well, I might need to look and inspect what's going on. I might want to be able to set breakpoints in different threads. We'll see an example of how one might do that. And I might want to switch from one thread to another, switch my focus, so to speak. And so CUDA command is used to inspect or set the current thread focus, okay? And I will demonstrate how to use this command when we go through our demo walkthrough, which is right now. So I need to change my sharing configuration. Let me stop and take a quick look at the chat. Does GOP on NVHPC imply -G2? NVHPC, I assume what you mean is the HPC SDK. I'm not really sure what you mean by that, but I think you mean the HPC SDK, and I don't know the answer to that question. Does line inflow influence the performance like -G? No, it does not, and this is one of the benefits of using line info. In other words, one of the reasons why I don't feel bad suggesting that you might just want to get in the habit of using line info all the time, so that if you need to debug or use compute sanitizer, or if you need to do some profiling, your code's already built correctly to do that. I don't personally have a problem with using that flag for production code. You might see that differently. If the -G turns off optimizations, yes, it does. This might impact the behavior of the execution. The error may not show up. That's true. And I talked about the idea that anytime you build debug code, it does change code generation, and therefore your error may disappear. And all I can do is say, I apologize. The tool's not perfect, but I do believe those situations are rare. Let's see. You know, there's other approaches to debugging, right? Just because something simple like the most obvious usage of the tool doesn't immediately get you to the solution, doesn't mean that you can't use other debugging approaches like divide and conquer, right? Binary division, bisection. These are standard techniques that are in no way unique or specific to CUDA. And so the entire topic of how do I debug computer code is certainly out of scope here, right? I'm assuming that you have some ability or some interest to learn about how to debug code, and I'm not going to cover every imaginable topic. But if the tool pans out for you, if the tool doesn't pan out for you for some reason, you probably still have other methodologies that you can use, like divide and conquer, or in-kernel printf is another one that people use a lot, right? I'm not covering it here. It's pretty obvious, but you can put a printf statement in a kernel, and you can debug code that way. Let's see, what other questions do we have? These tools also work for non-CUDA models such as OpenACC, yes. OpenCL, no. Okay, OpenACC, yes. OpenCL, no. Yes, CUDA GDB works on OpenACC, yes. OpenCL, no. Since behind the scenes, OpenACC kernels, okay, that's not a question. Okay, it looks like I've covered the questions. What about OpenMP target offload? OpenMP target offload generated by which compiler is the first question that I would have to ask there. Okay, if it's a compiler from NVIDIA or PGI, in other words, a subsidiary of NVIDIA, I think it will be supported. If it's somebody else's OpenMP compiler, I'm not so sure. Okay, let me push on with the demo because we actually probably have just enough time to get through the demo now in our 2-hour slot here. Okay, so as I mentioned, I need to switch my sharing configuration. So I'm going to briefly stop sharing and then share my screen. So hang on just a moment. And we need to switch to my terminals. So I have a couple terminals here onto a machine that has a Tesla V100. So that should be more or less comparable, at least as far as that GPU goes, more or less comparable to the GPUs that you would find in Summit, for example. And as I mentioned, this CUDA GDB or CUDA GDB is referred to as a source level debugger. And so it's going to be convenient for me to have my source code open and something that I can inspect and get line numbers from while I'm debugging my code. So in the left-hand terminal pane, you can see that I have a file open, and this file has just a small amount of code in it, right? This is my kernel, and you can see that I have a device function that's called from the kernel. Not a whole lot of code here. I will point out that this code, this kernel code, this is very similar in a variety of ways to the homework problem that I have given you. Okay, so if you understand how to follow through the debugging steps here, I think you're going to be well on your way to understanding how to debug the homework problem. So it's convenient for me to have this open. Now, as we talked about, when we get started with building, we're going to want to make sure that our code is built using debug switches. And so I'm going to do that right now. My code is something called T887. So I'm going to build my code. I'm going to say nvcc-arch equals sm70-big G little g T887.cu, and the output is going to be in T887. Okay. So hopefully this builds correctly. It's just the code that you see on the left-hand side. So let's take a look at this code on the left-hand side. What's going on here? First of all, we are in each thread populating shared memory with a value that is nothing more than my standard globally unique thread index. This is nothing other than threadidx.x plus blockdim.x times blockidx.x. That's your most commonly used one-dimensional globally unique index. So thread 0 has a value of 0 for that. Thread 1 has a value of 1, and so on, okay, up to the size of my grid. The threads in block 1 are going to start at, in this case, my block size is 256. So the threads in block 1 are going to start at 256, 257, 258, and so on. So each block is loading its shared memory array with these linearly increasing values. And then I'm doing what amounts to, through a function call, I'm doing what amounts to a very trivially simple shared memory sweep style parallel reduction. In other words, I'm adding together all of these values. So what is this kernel doing as a whole? As a whole, this kernel is doing the computation of the sum of the first n integers, where the n is the size of my grid, okay? And so that's a number that's easy to compute, and our host code will compute what that should be, and it will tell us if we're not getting the right answer. So let's just go ahead and run it. Not going to be that exciting. Does this code work with compute sanitized? Yes, it does. Another good thing to do. It's one of the prep steps that I told you about. Sanitizer. Okay, there's no errors reported. So in fact, this code has no defects. The output is matching, okay? Towards the end of the presentation, we'll inject an error in here, but it'll be sort of a catastrophic error. But nevertheless, we're going to learn how to use the tool anyway, just by inspecting the behavior of this code, okay? And when you get to the homework problem, you'll have a homework problem that actually does not compute the correct answer. And so you will actually need to debug that using the methodology and the tool that we're describing here. So it's a pretty simple code. And what we want to do is just learn how to use the tool with this code. So when we're getting started with CUDA GDB, The first thing that we're going to do is run the CUDA GDB tool. We're going to give it the name of our executable. And typically, the first thing that I might want to do, there's a variety of different ways that you can debug code, but one of the ways to debug code is just to start at the beginning and look at the behavior and see if you spot anything that appears to be going off the rails. So we might want to set a breakpoint in our kernel code. We expect that this kernel is going to run and be launched. You might want to set a breakpoint. And let's pretend that I'm not really paying close attention here. And so let's say I wanted to set a breakpoint on this line. Well, down here at the bottom, it's telling me I'm on line 11. Okay. So could I just set a breakpoint by saying break line 11? Yes, I could. Another way to specify a breakpoint is to say break and the file name t1887.cu:11. Those are equivalent syntax in this case. And the reason that I'm pointing this out is because if you have a code that's built from multiple modules, i.e. multiple files, then you'll probably need to use the file name syntax. But in this case, I could just as easily say break on line 11 because it knows that there's only one module associated with this code, okay? So I'm gonna set a breakpoint at line 11 and see what it does. That's a little bit weird because it's a blank line, but it does sort of appear to be the first line of my kernel code. And strangely enough, it's telling me that it set a breakpoint at line 19. This is not line 19, so I suggest you just ignore that, okay? Now, the next thing that you'll want to do is actually be able to run the code. So the first command, or the second command I'm going to teach you after the breakpoint command is to say R. R means run, and specifically it means run from start. In other words, run your code as if you were launching it for the very first time. It doesn't mean pick up where you left off. It doesn't mean continue after the breakpoint or anything like that. It means run from start. So if you issue it later in your debug session, GDB will ask you, do you want to start over, basically, okay? So we're going to learn another command to pick up where we left off. But I did do the R command, okay? And no surprise, we hit a breakpoint. One of the things that you might want to notice is, in addition to just saying a breakpoint was set, it also gave me a breakpoint index of 1, okay? You can have multiple breakpoints in your code, and one of the ways that you can distinguish amongst those breakpoints is by their ID. So when we hit this breakpoint, it's telling us that we hit breakpoint 1. That's not really a surprise. It's the only one. Notice also it's giving me some other useful information, like what was my kernel launch configuration and what was the numerical value of the parameters that were passed to the kernel and what was the actual line of code that I stopped on, okay? So now we're seeing something that looks sensible. We stopped on line 13, which is this line right here. And I'm going to suggest to you that's realistically the first line that you could stop on. Okay, this is really just a declaration. That's not necessarily code or anything that's executing there. So the first line that we could reasonably stop on is line 13. And even though I set my breakpoint on 11, it's saying it hit breakpoint 1. And instead of telling me you're stopped on line 11, you're actually stopped on line 13. In addition, it's telling you what is the contents of line 13, okay? So this is nice because I have source level debugging. So in the command line, it told me what does line 13 look like? And sure enough, that matches what I see on the left-hand side. Okay, as I mentioned, you can have multiple breakpoints, okay? So let's, shoot, I've already messed up my script. Okay, let me get out of this. So quit is the command to exit GDB. If you have a debugging session in process, meaning you're stopped, then it will ask you, do you sure you want to quit? I want to quit. I'm just going to start this session over again. And I might want to set my breakpoint at 11 like I did before, okay? But a new thing that we want to learn about is hitting a conditional breakpoint or setting a conditional breakpoint, okay? So I'm going to run the code and get up to where I was before. And now what I'd like to do is change the behavior of that breakpoint I set to make it conditional, okay? In other words, I want it conditional on something that's going on in my code. So a conditional breakpoint works like this. I type the command condition, I give it a breakpoint ID, and then I say the condition that I want to be true in order for this breakpoint to be hit. So the condition that I want to be true is I'm going to go to my next line of code, okay, where we see b equals block idx.x. And I know that block idx.x is a variable that's unique for each block. And so the threads in block 0 will have a value of 0 for that. Threads in block 1 will have a value of 1. Threads in block 2 will have a value of block 2, b2, b equals 2. So let me go ahead and set a condition, b equals 2. just like you would type that in C or C++ code, okay, double equals. So when b equals 2, when that Boolean expression that I have given evaluates to true, now my breakpoint number 1 is no longer an ordinary breakpoint, stop always. A conditional breakpoint means stop, check the condition, and if the condition is true, then stop. If the condition is not true, continue execution. Okay, so I've now changed the nature of this breakpoint, and I want to introduce yet another command, which is called the continue command. Okay, so the continue command is C, and this means pick up where we left off. I wouldn't want to use R here, or I could, but I don't think I want to, because R starts from the beginning. C means pick up where you left off after the last breakpoint and continue execution there. Okay, now let's see what happens. Okay, the code exited. Okay, and the reason the code exited is because I was at a point in my code where that condition never evaluated to be true, or I never hit that breakpoint line. Okay, we'll come back to conditional breakpoints. In fact, I need to do it right now because I'm done. So let's start over and debug again. And let's set a breakpoint now on line 15. Okay. B15. So that's a different line of code. Okay. Line 15 is here. Okay. That says int IDX equals that expression. That's setting up my globally unique index. Okay. And if I do this, then it's telling me there's a breakpoint at line 15. Now let's set another breakpoint on 11, which I had been using before. We now know that this one is breakpoint number 2. Now let's run. And we see that we hit breakpoint number 2 this time. Okay. And we're on the same line of code that we were before. Now let's change the condition on breakpoint 1 to what I had before. Breakpoint 1 is now set on line 15, whereas I'm stopped on line 13 here. Okay. Now let's continue at this point. And you'll notice this takes a little while. That took a few seconds anyway. But now it tells us that we have hit breakpoint number 1. Okay. Now I want to draw your attention to some other information that it is printing out as we hit these breakpoints. The other information that we're hitting out is that each time we hit a breakpoint, it tells us what our focus is. Okay, switching focus to CUDA kernel 0, grid 1, block 0, thread 0. Okay, lane 0, which is the same as thread 0 in this case. Okay, so when I stopped previously on breakpoint 2, I happened to stop. That breakpoint was hit or declared to be hit on the first thread in my grid. But now, because I hit this conditional breakpoint can only be true in block 2. Okay, so now as a result of hitting this conditional breakpoint, it has switched my focus to thread 0 in block 2, which is the one that hit that breakpoint. And once again, I'm on line 15, which is what I would expect. Okay, now let's learn about another command called the S command, the step command. Let's see what that does. So I'm on line 15 now, and let's S, so we step, and sure enough, it advances one line. So after line 15, int IDX equals that. The next line of code over here on the left is the line of code that's populating shared memory. And so that's saying S of t equals IDX. Now, an important thing to keep in mind is that when it prints out this line of code, it has not executed that line of code. When I hit a breakpoint or step, it means that I stop on that line before executing that line. Okay. Let's continue to step and see what happens, because we're going to learn that there's a different ways to step. So now when I step, I see that the next line of code that I'm going to execute is this function call to function myReduce. Okay. So I'm on this line of code now. I'm about to execute this line of code, and that line of code intends to call this function. Okay. So let's see what happens when I hit S. Notice now that it's telling us the line of code that it stopped on is line 5. And in fact, it nicely informed us that, hey, you're in this function called myReduce now. Okay. And it's telling you what the parameters were to myReduce. The variable smem was set equal to that value. And we're at line 5 in the source code. And it's telling you what that line is. Okay. And we can confirm that just by seeing what's going on over here. This is the first line of that function, and there we see it over there. Okay, so this, I would refer to the S command as a step into command. I refer to it as step into to let you know that when you use it, if you call a function, it will step into that function. In other words, it goes to the next line of source code, wherever that may be. Okay, that's what the S command does. All right, let's learn a new command now, and let's talk about printing data. And I know that I have this data called shared memory, and it lists an array S. And so I wonder if I can use the print command, which is P, to symbolically print using variable names, just like I would in C or C++. The answer is yes, but it doesn't work that way because there is no symbol S in the current context. Right now, I'm in the context of this function, and so I can only reference symbols that are valid in that context, and there is no S symbol. But the equivalent symbol, S, gets passed as my parameter smem, okay? So could I do the same thing with P of smem of 0? And the answer is yes. And now I see that I'm in block 2, and I asked for the value of the shared memory location in location 0, and that was populated by the first thread in block 2. Block 0 handles 0 to 255. Block 1 handles 256 to 511. And block 2 starts with 512. So it's no surprise that shared memory here has the value 512 in it. Okay, and I can inspect other things as well, like I can inspect other locations in shared memory, for example, if I wanted to. And yes, as I move forward in shared memory, higher threads are populating that, so we see higher values. Okay, what if I wanted to print the value of I? I see that I is a variable listed right here. Okay, it's on the line of code that I'm about to execute. Can I print I? No, we get a different kind of message here that says it's optimized out. Now, when you see the optimized out message, you should be aware that it probably means that you're, again, in a scope situation, and you're probably asking for something that doesn't exist but may exist later. And in fact, the variable I is only valid in the body of the for loop, and we haven't started to execute that yet. So let's go ahead and step forward. Now we're at a line that's in the body of the for loop. This is on the first line of code in the for loop, the sync threads. And now if I try to print the I variable, I get a sensible number. Why is it 128? Well, it starts with the block size, which is 256 shifted right by 1. And that is indeed 128. So we're getting an expected value there. Let's go ahead and step forward one line. Okay. And we see that we are now on line 7, and this line 7 is if thread idx.x is less than I. Okay. And at this point, I might have convinced myself that what I'm interested in inspecting is not happening inside this function call. I want to get out of this function call. Okay. So the way that I would get out of this function call at this point is to go ahead and set a breakpoint on the line of code on the left-hand side. I've moved over here. This line of code happens to be line 18. Okay, so at this point, let me go ahead and set a breakpoint at line 18, B18. Okay, and now let's continue. And now what we see is I'm broken at line 18. Okay. Note that we have a change of focus again. I didn't use a conditional breakpoint this time. And so once again, it has bumped me back, so to speak, to another thread in block 0, but this time it happens to be thread number 32. Why is it thread number 32? Well, this is where we're going to start to learn about this idea of multi-threaded debugging. And so I want you to hold that thought. We're going to unpack this towards the very end of this demo. Okay, but it's curious and interesting that it chose to declare this breakpoint being hit on thread 32 instead of thread 1. We're going to discover why that is eventually. Okay, but let's continue our journey here of learning commands. Okay, so now that I have hit this breakpoint, I can take a look at shared memory again. Now I can do PS of 0 because the S variable is in scope here. And I see that S of 0 now has some other value in it because we've now completed sort of the reduction. And so the values are much bigger now in shared memory because they each represent a bunch of values that were added together. Okay. When I'm printing out variables, another thing that I can do when printing is print out multiple members of an array at the same time. And the syntax to do that would be to use, after my print command, would be to use the @8 command. Okay. So now I'm printing not just the first value in the array called S, but I'm printing 8 different values, the first 8 values in the array called S. Let's now learn about changing focus, because right now I'm in block 0, thread 32. If I ask for variables, they're going to, to print things out, it's going to be consistent with thread 32. And so the shared memory that I'm reading here is consistent with the shared memory associated with block 0, because that's my focus. Okay. Could I inspect at this point the shared memory in block 2? Yes, I could. And one of the ways to do that would be to simply change my focus. So I'm introducing the CUDA command. And when you want to change focus, the only thing that you need to specify is the focus that you want to change. So if I only want to change the block, I can simply say block 2. If I only wanted to change the thread and stay within the block, I could say CUDA thread 0, for example. Then I'd end up in block 0, thread 0. But in this case, I want to inspect shared memory in a different block. So I'm going to say CUDA block 2. And when I do that, it's going to tell me it switched its focus to block 2, but otherwise the focus is unchanged. So I'm still on 32. And interestingly, I'm on the same line of code as well. Doesn't have to be that way. We're going to see an example where we won't see that. Okay, but for the moment, notice that the current instruction is printed. Okay. Now, if we print shared memory, the same command that we used before, we get different values. And that should be no surprise, because different blocks start out with different numbers. So when we sum them, we end up with different numbers. And in fact, when we go from block 0 to block 2, we're summing larger numbers. So the partial sums that are left over in shared memory at this point represent partial sums of larger numbers to begin with. Okay, at this point, we're done with this session, and I want to start over with a new session and learn some new things that basically require me to start over. So I'm going to hit C at this point. I hit another breakpoint that I hadn't cleared, but eventually, if I keep hitting C, the application terminates. I know that it terminates because I'm back to host code now, printing out my result. Okay, and also it tells me that the thread exited normally. So let's get out of CUDA GDB using the quit command. This time I don't have a debug session in progress, so it doesn't ask me if I'm sure. It just quits, and we'll start over again. And we're going to learn a few different commands. So we're going to set the same breakpoint that we had before. We're going to hit R. And now, what if I wanted to delete that breakpoint? There's a couple different ways to delete a breakpoint. The command I'm going to teach you is delete. And delete uses the breakpoint ID. So this is breakpoint 1. So if I say delete 1, it'll delete that breakpoint. The other command, which I'm not going to spend any time on, is called clear. And clear, instead of taking a breakpoint ID, takes a line number. So you'll notice that I set the breakpoint using the B command with a line number. I could have said clear 11. Okay, now that breakpoint doesn't exist anymore. But if I hadn't done the delete 1 command and I said clear 11, that would equivalently clear the breakpoint that I just set. Okay, so now let's learn another new command. So let's continue stepping through this code for a few times. And now we're at this point where we're about to enter the function. And remember, once I was in the function, I was sort of, buried in the function, and to get out of the function, I had to set a breakpoint. Well, if I think that I don't really want to enter a function, I would just like to go to the next line of code after the function call. There's a command to do that too, and that command is called N for next. Okay. And so what next does is, instead of going to the next line of source code wherever it is, it goes to the next line of source code in the current module that I'm in. Okay, so in this case, what we mean is, if I'm on this line, the next line of source code, wherever it is, would be this for loop. We saw that already. But the next line of source code in the current thread, so to speak, is this if statement. So if I do a next command at this point, I'm going to be expecting that I will see the if statement printed out. Okay, and so now I went from line 17 to line 18. Okay, and notice that once again, it switched focus on me. So what's going on there? Okay, why is it switching focus? Well, it's switching focus. The proximal reason is that was the first thread that got to line 18, the line 18 that you asked to go to. Okay, so block 0, thread 32 happened to be the first thread that got there, so to speak. And so we have stopped at that point. Now, this is, again, another clue that's going to lead to us understanding some important stuff about learning how to debug in a multi-threaded environment. But we're going to continue. So now I notice that I'm on thread 32. Well, I don't want to be on thread 32. I could say CUDA thread 0 and switch my focus, okay? And now when I switch focus, notice that something weird has happened. What has happened is, in addition to switching focus, my instruction pointer changed. I'm on a different line of source code now. What is going on? This is very strange. Okay, let's unpack what is going on. Let's go back and look at our code on the left. Remember, I said I have a fairly standard sweep style reduction, shared memory sweep, parallel reduction. And the nature of the parallel reduction is that I'm conditioning thread behavior with this for loop, okay? So, and also with this if statement, okay? So what this if statement does is it basically selects fewer and fewer threads. Each time I go through the for loop, the first time I go through the for loop, I'm going to select the first 128 threads to do this. The second time I go through, I'm going to select 64. The next time I go through, I'm going to select 32, and so forth, okay? So what it's telling me is that the thread 32, which is in the second warp, is the first one to hit this. But then when I switch to thread 0, it's somewhere else. So thread 32 got to here. Well, thread 0 was still here. Okay. So this is something that if you understand what's going on here, it will explain most of the things that we have tripped over already. Okay. And it's also going to lead to some more observations that we want to make about parallel thread debugging or massively multi-threaded debugging. Okay. Is that when I switch from one focus to another, I could be in a more or less completely different place. That's something to be aware of. But nevertheless, I did switch my focus to thread 0. Okay. Let's see. So I did CUDA thread 0. Okay, now let's step forward on thread 0. So now thread 0 is executing this for loop. Apparently it had one more iteration of the for loop to do. And now it has gone to the end of that for loop at line 8. And now we see that I am out back at my main routine, my K routine, so to speak, my kernel code, my main kernel code. Now let's print block vals. Block vals as we see, block vals is that global memory location. This is the parameter that's passed to the kernel, block vals. Okay. And basically each block is writing its partial sum to a particular location in the block values array. And that block value location is given my B, which is my block index. So thread 0 writes to location 0, thread 1 writes to location 1, and so on. And in each case, I'm asking a single thread to write S of 0. In other words, the first location in shared memory to my block values after the reduction is complete. Again, this is all pretty standard parallel sweep reduction stuff. Okay. At this point, if I print block values, what do I see? I see a value of 0, even though I know that I have something else in shared memory. What if I print out shared memory of 0? It's a different number. Okay. Just briefly, let's take a look at, well, let's step one more time. Okay. And so if I step one more time, I see now that thread 0 is at line 19, which is the end of the kernel code. And now let's print block values of 0. This means that the previous line is already executed. And I see that it has the correct value in that global memory location. A few other commands here. Info CUDA devices. This is one of the ones that we talked about already. Sorry, device says. And I see that I have 4 GPUs in this machine, 3 of which are Tesla K20Xs, one of which, the one I'm working on, is a Tesla V100. So that's the info CUDA command. We can also do help info CUDA to find out what are some other things that I can ask about. So I can ask about devices, SMs, warp, lanes, etc. That's enough for that. Let's continue, and we'll quit one more time, and we'll do one more session. Okay, so the last session we're going to do is now we're going to inject a defect. And so in my code over here, I'm going to make this say B-1. Okay, so now I've caused each thread or each block to write to a location of B-1, and obviously block 0 is going to try to write to location -1, which is illegal. Okay, and so this demonstrates another way to use CUDA GDB, which is simply to kind of localize an error, find out which line of code is causing an error. Okay, so I need to save that. Right, and over here, since I've exited, I can just rebuild the code. Let's run this code like we did before, and I get a kernel exec error. So in this case, because I indexed -1, that's something that the runtime can catch. So an index of -1 on an array is actually stepping over an allocation boundary by definition, and it will be caught by the runtime. But if I had done +1 instead of -1, I would not have gotten an error. In fact, we can do that. Let's do that. This is also not correct. Okay. Let's compile that code and run it. And I simply get a result that doesn't look correct. Okay. But if I run this under Compute Sanitizer, I get errors. Okay. Invalid global write of size for exactly one error. That's exactly what I would expect, because there was one block that's writing to an out of memory or an out of bounds location. But can we use CUDA GDB to do this? Again, I would prefer to use Compute Sanitizer to do this. Notice that if I compile a load with a code with -G, I also get the nice handy line number information from Compute Sanitizer. So -line info or -G will give you this additional information, very useful. But let's go ahead and do our last quick debug run through, and that will probably end our session. So we have rebuilt the code, and we're going to start up CUDA GDB /D1887. And we'll run this code and just see what happens, okay? Oh, that was dumb. Well, I did, oh, that's not the right executable. Okay, now let's run this code and see what happens. Now what happens is I get no error, okay? And so now let's do help set CUDA. And help set CUDA says that I can set, one of the things that I can set is memcheck. Okay, so let's do set CUDA memcheck on. Oh wait, I have to start over now because the code's already complete. So let me start the debugging session again, now that we know that. And let's do set CUDA memcheck on. And now let's try the same experiment. And this time, instead of just letting the application run to completion, because we've enabled the memcheck capability, CUDA GDB will also report the error. And notice the error occurs in block 3 only. That's where I would expect it to occur, because the last block is the only one that's indexing out of range. Okay. Okay, that pretty much completes the walkthrough of CUDA GDB. Since we seem to have just a bit of time, what I'd like to do is repeat a previous session, a previous walkthrough that we did very quickly, and show you a little bit more about the thread execution behavior. It's something that we've already sort of covered, but I want to just focus on it or emphasize it. So let's debug this thing one more time. So let's build the application the way that we had it before. I don't think it's going to matter, but so we're going to build our application with the way the code started originally. then we're going to start debugging. And we're going to set a breakpoint on line 11. Doesn't have to be there, it could be 13, but we're going to run. We hit our breakpoint on line 13. Let's go ahead and delete this breakpoint. We won't be needing it anymore. And what I would like to do is get to the point where we were at thread 32. So we're going to step all the way through this code. And at this point, we're going to do end, so we skip past that. And now we're at thread 32. And let me repeat what I did before, which is I stepped this thread forward. Remember what I did before is I printed the block vals of 0 in this case, because I'm in block 0. Okay, and block values of 0 is 0, but the shared memory value that I'm about to assign there is not 0. Okay. And now let's go ahead and step one more, just like I did before, but notice that I'm in thread 32 now. And now thread 32 is at the end of the code. And I might make the mental error that says, oh, I'm at the end of my kernel code, so now block values should be correct. Well, is it? No, it's still 0. What happened? Okay, what happened is that thread 32 got to the end of the kernel before thread 0 does. And thread 0 is the one that's actually updating the block values. And so now if I say CUDA thread 0, we'll see that thread 0 is still somewhere else. It's not done yet, even though thread 32 exited. Okay, and now just like I did before, I could continue to step in thread 0. And eventually I will get out to thread 0, executing the last line of kernel code. And now if I run or print block vals of 0, I will get a non-zero value. All right, so that's it for the CUDA walkthrough. And I'm going to go back to my slides now and just cover a few last comments. That was the demo. The sync check tool, I think I may have covered this already. The sync check tool may have limited usefulness due to the Volta execution model. CUDA Fortran debugging with print commands at the moment is not working correctly. And so you basically can't use the print command is my observation, but there are internal bugs at NVIDIA to get this fixed. And so in CUDA Fortran in the future, a future tool chain should have this fixed. You are not able to inspect device memory unless you are stopped at a breakpoint in device code. We didn't set any breakpoints in host code, but if I set a breakpoint in host code, you could do that. CUDA GDB allows you to debug host code as well, exactly the way you'd use GDB to do it, essentially using all the same commands that I used here. But if you're stopped at a breakpoint in host code, you will not be able to inspect device memory the way that we did it. Also, we're going to be improving the compute sanitizer host backtrace in the future. One of the last things that I wanted to demonstrate was how to look up an error code. So you might be debugging an application where they've been a bit lazy and they just spit out the error enum type as an integer value. They didn't bother to do CUDA get error string. And so you might want to know, well, what is error number 719? There's a couple different ways that I can think of to find it. Okay. One of them is to look in on a machine that has CUDA installed, like this one, or let's use this one, the one that we were just using. Let's get out of CUDA GDB. And there's a file called user local CUDA include driver types.h. And so it's there. And so if I edit this file, or I could really just grep it, but I want to use an editor so I see more lines. And now if I just search on 719, there it is. It's called CUDA error launch failure, and it tells you the text before this error tells you a pretty long description of what's going on with this error code. Okay, so that's one of the ways to get the error code. Another way to get the error code is to use the runtime API documentation. So let's do that. Where is the runtime API? It's in the documentation where everything else is, which is at docs.nvidia.com. I'm interested in CUDA toolkit documentation, want to browse that. Now we see the documentation probably that you're familiar with. We're going to go to the CUDA runtime API. And what did I say about where to find it in my presentation? Runtime API section 6.36 data types. So section 6.36 data types used by the CUDA runtime. And what I have to look at is the CUDA error T enum. CUDA error enum. And here you can see they're all listed in order, and each one has a text description. So if I scroll all the way down to 719, I should see something similar to what I saw before. So the CUDA runtime API documentation also has all the error codes listed, and there's 719. Okay. Okay, that actually does bring me to the end of my slides. I have some topics in here for further study, and like we've done before, there is homework. So I apologize, we're just about out of time. I will take a quick look at the chat, but I don't know that I'm going to have time to answer many questions, but I will do that right now. Let's see. How do I print within a kernel? You use printf just like you would in host code. Okay, that's how you print within a kernel. Yeah, sorry, I didn't clear the terminal each time. The manual says CUDA watch points are not supported, and that appears to bring us to the end of the questions in the chat. So they're basically all already answered. So we are at the end of our session for today. I hope you found it useful, and I hope this will be beneficial for you in your CUDA journey whenever you have to deal with code that is not bending to your will. So with that, I will wrap up for today, and thank you all for your attention and sticking through this for 2 hours.